Suppose there are finitely many primes, which means we can list them, 2, 3, 5, all the way up to the very last one. Now, let's multiply all these prime numbers together and add 1. That gives us a number that is bigger than any of the primes, also bigger than 1. But it's 1 more than a multiple of 2, means it's not even, which means it's not divisible by 2. It's also 1 more than a multiple of 3, so it's not divisible by 3. It's 1 more than a multiple of 5, so it's not divisible by 5. And in fact, it's 1 more than a multiple of any prime, which means it's divisible by none of them. So we have a number that can't be prime, or 1, but it also can't be composite because it's not divisible by any primes. But a number can only be 1, prime or composite. So the only possibility left is that the assumption must be wrong, the assumption that there were finitely many, which means there are infinitely many primes. This proof is 2,300 and some odd years old. Comes from Euclid, as in Euclid's The Elements, Euclidean geometry, that ancient Greek. 2,300 and some odd numbers of years old, and it is still a valid proof with a valid conclusion that we can still use 2,300 and some odd years later. In fact, the method of proof, proof by contradiction, is still a textbook proof strategy. 2,300 and some odd years later, everything about this proof remains valid and relevant. So what does this say about math? Well, it says, among other things, that even when new math is discovered, created, whatever you want to call it, the old math, as long as it follows the same rules as the current stuff, remains just as valid as it ever was. We can build on it. We can use it. We can refer to it hundreds, thousands of years later, and it's fine. And when we discover something new, we don't have to upend the old, as exciting as that can be. I mean, take Darwin. Before Darwin, who would have thought that species can change over generations? Take geology. Before they knew what was going on inside the atom, and that the sun had a way of having power for billions of years. Who could have thought that the Earth could be as old as that? And in 1905, Einstein came up with this thing where if the speed of light is the same for all observers, then time and space have to change. But in math, you don't have to throw away anything old. Well, math does experience the occasional paradigm shift. It just doesn't have the same kinds of upheavals. I mean, take high school math, calculus. Most of what you would learn in calculus was established, well, we're talking Newton and Leibniz, we're talking early 1600s, think Shakespeare, forsooth, and all that. It's not new. And even if you get to multivariable calculus, which not many high schools offer, that, you know, that ends in the mid-late 1800s. There's basically all of these stuff that you're expected to learn, and most of it for actual reasons. I mean, there's some discussion to be had about what's taught in which order to whom and when, but basically hundreds of years later, and thousands in the case of geometry, we it's still relevant. We still teach it for actual reasons. So anyway, take from it what you will. Hopefully at least you find it interesting. Bye now.